I will share with you a short video on the next part that is related to machine learning system design. As you probably have already guessed from my screen, we will be discussing loss functions. We will be touching upon regression, then classification, and then finally ranking losses. So first of all, should I even tell you what's the loss function? Conceptually, loss function is a measure on how well the model that we are training is approximating the data that we have. So to do that, to approximate this, to get an answer to the question how well this approximation works, um, well, to just answer this question, we can actually use many different functions, and we are. It can be like CTR might be a way for us to identify how we are doing. So we were discussing some of those ways in evaluation section. How loss functions are different? Well, loss functions are differentiable. Why is this important? Because if loss function is differentiable, and if your model has some inputs and then those inputs propagate through the model up to the level of making an actual prediction, and then you compare this prediction to the data that you have, to the label that you have, and then you can figure out the error, then this loss function, if you find a derivative for all of the ways that you have, if you can derive this derivative, then you can do a gradient descent. So the gradient descent here would be an optimization in the space of all the possible functions, given that you have fixed the structure of this function, to the function with the specific parameters that are the most optimal for your particular use case. So we will be discussing today those loss functions, and all of those loss functions will be differentiable so that you can improve the model, so that you can find those derivatives and weaker weights, making steps in the direction opposite of the gradient so that your loss decreases until you find something close to local optima or global optima. Okay, so we will start with mean absolute error. And you can see that all of those functions are already drawn in the slide. So this is mean absolute error. You can also easily find it on the plot. So it's this yellow one. Why would we need this function when we also have the mean squared error, right? Those are pretty similar. Obviously, the only difference is that these square don't exist here. We are just taking an absolute difference between the true value and the predicted value. Just to be clear, we are discussing the regression right now. It's important because let's say you have some like log normal distribution, so like this, with a long tail, right? And you want to make predictions. What will happen if you try to make these predictions using mean squared error? Mean squared error will be optimizing for the mean value of this distribution that you have. But, or maybe mean is closer to this side, but I'm not sure. But mean absolute error will be optimizing for the median value. So why one is mean, one is median? So here for this mean squared error, you're squaring all the errors. So it means that the bigger the error, the more important that becomes. So it tries to optimize for all of those tail errors down there, so that it tries to adjust so that those errors are not as big, right? So you are basically making more, or yeah, vice versa actually, right? So mean will be closer to this side. Yeah, I think it's both actually. So the thing is that for mean squared error, you will be dependent on outliers, and then like how big is the outlier can tweak the results of your optimization, cannot affect the results of your optimization. So in some case here, i- if you compare this function to median, it will be closer to this like mode that we have, right? Because we have more values here. But on average, basically it targets the value that on average your error will be the smallest one. But the mean absolute error targets the median value, because if you find a derivative here, right, it will be 2 times error essentially, and here it would be just 2. So the size of the error affects mean squared error, but it doesn't affect oh no, actually not even 2, right? It's not squared. So it doesn't affect this absolute error in any way. That's why you might want to use mean absolute error instead of mean squared error. It's less sensitive to outliers, and it will target the median value for you. This will be important when we will be discussing other losses here on this slide. Let's actually do that now. So what's the problem with, for example, mean absolute error? The problem is that it's not differentiable around 0, um, because it's a sharp corner there. And you can tweak that, adjust that, so that you have a more stable behavior around 0 for the convergence of your function. So in this case, you will use something like Hubert loss, which is essentially a combination of parabola and linear functions. So it still has the same linear tails here and here, but in the middle, it repeats the parabola. And that's it. That's the main important part of the Hubert loss. Then for quantile loss, it's more similar to mean absolute error, but instead of targeting the median, it targets a specific quantile. So here is the quantile that we are targeting. So it's trying to optimize for a specific ratio between underestimations and overestimations that we are making. So as you can see here, for example, right, we are there is a bigger penalty, and the error grows higher for the overestimations than for underestimations. And that's essentially it. So if you need to predict, let's say you need to predict ETA for delivery, you will probably want to predict a specific time, but in the beginning you might be optimistic so that the person doesn't drop from making the order. In this case, you might want to predict, I don't know, like 30th percentile or median. But maybe afterwards, you want to be pessimistic in your predictions, and then maybe you want to predict 80th percentile of delivery, so that on average, 80% of people will get the order earlier than your prediction. So that's up to you. But then you have like different thresholds for which you need to make the prediction, and then here the quantile loss will be useful. Okay, let's go to classification losses. So for classification, um, if we guessed correctly, we want loss to be as small as possible. But if we guessed incorrectly, the closer we get with our probability to, for example, to incorrect guess, the bigger we want our loss to be. So the main and the most the most widely used one function is this binary cross entropy. But it also has other names, so logistic loss might be one of those. And also you can, if you are using this function to do ranking, you can do that. Then it will be pointwise loss. Okay, now regarding this function, there is actually a nicer way of writing this, which is very similar to this function. So this function it's a categorical cross entropy. It's basically a multi-class binary loss. Well, it's impossible to have a binary multi-class ROS, but it's extrapolation of binary cross entropy to a scenario where you have many classes. In this case, you still have the same value here, right? But where does this value disappear? The thing is that this value is only true when the y is 0. So it's only true then there is a false, like a negative example. So in multi-class, let's say you have 3 classes, right? So if this class is the correct one, then we want to calculate loss for this function. So it will be basically log p1. If this class is correct, then we just want to do log p2. If this class is correct, we just want to do log p3. This will be our loss function. But over the data set, there will be cases when this is correct, this is correct, this is correct. So we are summing over many such cases. And then, yeah, we multiply by y, but only one y will be correct at a time. So eventually, it all comes down to sum of log of p true. So basically, whatever is the true class, you take its probability, then you do take a logarithm, and then you sum over all the possible values. So that's a nicer way to write this function, and it extrapolates to all the other things like binary cross entropy, categorical cross entropy. So that's how I like to remember it. Now, hinge loss. Hinge loss is a function that is used to maximize the distance between, like, let's imagine that you have your points, right, of 2 classes. Let's say you have a green class, and let's say you have a blue class. So if you have a straight line that you need to draw, then basically, if you want to maximize the distance between green and 0 classes, so you will draw something like this. This will be the separator that has the biggest possible distance, has biggest margin to different classes, at least in cases where it's separable. And that's what hinge loss does to you. It's used in things like support vector machines, right? That's the whole idea there. But then let's discuss, I don't know what else can I say about this loss, but the next focal loss is actually a very important one and very useful one. So you see this element here, right? And we have PT. So PT here stands for P true. So it's essentially the same thing as this, but we are also multiplying by this thing. Let's think about what is this thing that we are multiplying for. Why do we need it? So let's say PT, P true, like the true class, is very, very high. So it's a big value close to 1. So if it's a big value close to 1, then you do 1 minus value close to 1, you get a very, very small number. Then you take it to the power of gamma, and it becomes a very, very, very small number. So if you are sure, if the model is sure about a specific example, then it down values an importance of this particular example. It's very useful when you have, for example, unbalanced classes, or whenever you want the model to focus on the specific, especially hard hard observations. So that's what you can do there. You can use focal loss. It's usually the best case, best loss function for the unbalanced classes situation. And then finally, we have Kullback-Leibler divergence when it is used. So Kullback-Leibler is used when you have distributions and you want these distributions to be similar to each other. When do we need the whole distribution? So maybe, for example, you can use it in image generation or like diffusion models where you want to reproduce a particular distribution. So that can be a situation where you want to use something like this. Yes, variational autoencoders, I think, is one of the cases when you use Kullback-Leibler, because in variational autoencoders, you basically predict the whole distribution, and you need to compare to distributions. So there is a loss function for that. Also, in some cases, you might add it to your loss function if you want to compare specific distributions, like if you need to tweak your loss in such a way that one distribution is not too dissimilar from another one. Oh yeah, here the good example would be reinforcement learning, when you want to improve your policy, but new policy shouldn't be too different from the old policy. So you add this Kullback-Leibler part to your loss function, and it will push the new policy closer to the old policy so that you don't destroy a good policy with your update. Finally, let's do the recommendations. So in recommendations and ranking, you need to produce a list, and then there are many possible ways for how you can rank this list. And also in many scenarios, it can be, we can target different goals and different ideas. So point-wise, it usually works, but point-wise doesn't tell us that, like, all of these things are scored independently, and it doesn't tell us which particular item is better or worse compared to any other particular item. So here, right, we just do scores. Like for point-wise, as you can imagine, this is just the normal binary cross entropy. So either this is relevant or not. So the score will be between 0 and 1. And we don't try to target any relation between like those rows. So for example, if you just need to select one item out of many items and you're selecting those independently, then you can do that. But for something like when the whole list is important, you probably cannot use that, and you need to choose something more sophisticated, like for example pairwise loss or a listwise loss. So pairwise loss. Now, instead of just scoring all of those instances independently, you take a pair of those, and let's say this was clicked and this wasn't clicked. Let me use red here to be more explicit. So then it means that, okay, given the data that we have, this is truly more relevant. The first row is truly more relevant than the second row. And this was the correct prediction, right? But let's say then this was also clicked. Then it shows that we have put something on the second row and something on the fourth row was more relevant. So here we are inverting the ordering of those two things, which is not a good result. So how do we, given this information that we have, right? Let's say there were a few links that people clicked, or like a few desired outcomes that we have gotten from one list that we have presented, we can basically see all the impressions that we had. So here we had 4 impressions, and then we can create pairs out of this. So for each of those items, there we can pair it with like 1, 2, 3. The second item we can also pair with 2 and 3. The third item we can pair with the fourth one. And for each of those, we will have what we can call it pairwise loss, right? It's basically a probability given that we can give for scoring a particular item higher than another particular item or lower than another particular item. So here we will have some probability that the first item will be scored higher than the second one. And this was the correct thing, right? And we need to tweak our parameters even a little bit further in the same direction that put this first item here. But for, let's say for these two items, for the second and the fourth one, they were in incorrect order. So we now need to include this calculation into our pairwise loss. And it will penalize this situation when we are ranking something negative higher than something positive. And finally, when we need to calculate the whole, how good, how relevant is the whole list of items, and um, how relevant they are, depending on what are other items in the same list, then the problem is that the good metric for this is NDCG, normalized discounted cumulative gain, but um, it's not differentiable. And since it's not differentiable, then you cannot use it directly as a loss. But people figured out a way to do that, kinda. So you can just calculate the same pairwise losses and um, delta to NDCG metric if that would happen if you changed those two items in their places. And then you basically do, you calculate this directly. And thing is that here you don't have a loss function. So you don't, for listwise ranking, at least for this particular kind of listwise ranking, you don't have a loss function, but you can calculate those lambdas for a pair of items I and j. And then you can just pass it, for example, in PyTorch, you can pass it directly to this gradient parameter when you do a backward step, and it will work. So then you just need to figure out how to calculate this whole thing efficiently, but obviously there are already implementations in things like PyTorch, and this will kind of target NDCG directly. So even though NDCG is not directly differentiable, if you use this listwise loss, it will still work, and you can use it for your ranking. But yeah, this is everything that I wanted to tell you today about losses. We went through regression, classification, and now recommendation or / ranking losses. And next time, I actually want to give an overview on how the whole search works end to end, let's say in Amazon, right? I use this example to create all of those different steps, but I'm not showing this to you today because it will take a lot of time to go through that. So some other time. Thank you for watching, whoever is here today. If you're interested in this next part, please tell me, because I'm not sure if I need to stream that. I have created it mostly for my own understanding. But yeah, tell me if you would enjoy it. Thanks for watching, and